Alright guys, time to do some more videos. This one is on the fundamental theorem of algebra. Sounds very important, doesn't it? Alright, let's do an example. Alright, we are going to graph and solve x cubed minus 5x squared minus 8x plus 48 equals 0. We're going to use our graphing calculator and put it in. It's going to look like this. So when we look at this graph, we see a 0 here, and we see a bounce here. So there are two distinct solutions at x equals -3 and at x equals 4. Alright, so now I'm going to factor this sucker. And the graphing calculator gives you a hint, and I'm going to let you use it on some of these problems like this. Instead of having to list all the possible rational zeros, you can use your calculator, narrow it down, and we're going to factor this down. So let's just go ahead and go with the -3, and we're going to divide this in to the polynomial. Like so. Remember, we can do the synthetic division. We're going to take the 0 right here, and then we're going to add 1 and nothing is 1, and multiply. -3 times 1 is -3, and add -5 and -3 gives me -8, and multiply. -3 times -8 is +24. -8 plus 24 is 16. -3 times 16 is -48. 48 minus 48 is 0. We know it's a 0. We can see it on the graph. We've just confirmed that it's a 0. But what we've also done is if -3 is a 0, then x plus 3 is a factor. And the other factor is this, 1x squared minus 8x plus 16. And now that we're down to a quadratic, we want to see if we can factor this sucker further. And if there's anything that multiplies to get 16 that also adds to get -8, we can factor it, which there is. So this is x plus 3, and then this over here is x minus 4 times x minus 4, so I'm going to put a little squared. And that little squared tells us that this has a multiplicity of 2. It has 2 solutions at 4. That's why there's a bounce here. So if we were to list all the solutions, we would say x equals -3, it equals 4, and then it equals 4 again. So it has 3 solutions, and that's because it is a third degree. So third degree, 3 solutions. One of those is repeated. The one that's repeated we say has a multiplicity of 2. Because it's in there twice. Alright, let's do another one. Let's graph and solve x cubed minus x squared plus 16x minus 16 equals 0. This is a cubic function, so we know it's going to have at most 3 zeros. Let's look at the graph. So now we can see that it has one distinct 0 at x equals 1. And this means that there should be 3 total solutions, but we only have 1. What's going on with the other 2? Well, we're going to factor and solve now. We're going to use this 1 that we know, and we're going to divide it into the polynomial. Alright, so we bring down the 1. 1 times 1 is 1, minus 1 is 0. 1 times 0 is 0. 16 and 0 is 16. 1 times 16 is 16, and then that makes 0. So what this tells me is that one of my factors is x minus 1. And then the other is x squared plus 0x plus 16. And x squared plus 16 does not factor further, so this is the polynomial fully factored. And when we say equals 0, if we set this one equal to 0, obviously we would get 1. We already know that. And if we set x squared plus 16 equal to 0, we could say x squared equals -16, x equals plus or minus the square root of -16. Therefore, x is positive and negative for I. That's 2 more answers. We needed 3 total. 2 of them are imaginary. So this is third degree. It has 3 total zeros. 1 is real, and 2 are imaginary. So that leads us to your fundamental theorem of algebra, which says counting repeated and complex solutions, an nth degree polynomial has exactly n solutions. Sorry, left out the word degree. Okay, write that down, and then let's do another example. Alright, so how many solutions does 5x squared plus 3x to the fourth minus 6x to the fifth plus 7x to the third minus 1 have? I'm just asking how many does it have? You don't have to tell me what they are. You don't have to tell me what kind they are. All you have to do is know how many there are going to be. And we're just going to look at the degree. Don't be fooled. The 2 is first, but that doesn't make it the degree. The 5 is biggest, so the 5 is the degree. And if 5 is the degree, then there are 5 solutions. All right, now, this example says find all the zeros. That means all of them. When it says all, so the key word is going to be what they're talking about. And this one says all. That means all repeats, all imaginaries, all reals, all zeros of f of x equals x to the fifth minus 4x to the fourth plus 4x cubed plus 10x squared minus 13x minus 14. So it's already in standard form, and we can see that it's fifth degree. So that means we're looking for 5 total zeros. And the easiest way to figure out where to start is to use your graphing calculator. So graph it in the calculator and look at all the possibilities. Instead of listing your possible rational zeros, we're just going to cheat and use the graphing calculator. And here's what it looks like. I can see 1 bounce, which is probably going to count for 2, and then 1 cross through, which is going to count for 1. That's still only 3. But we know at least x equals -1 and +2. So we can use either one of these, and we're going to do some long division. I'm going to go with the 2 first since it's not repeated. And I'm going to do my synthetic division. We want to divide 2 into the polynomial, so we bring down the 1, times 2 is 2, minus 4 is -2, times 2 is -4, plus 4 is 0, times 2 is 0, plus 10 is 10, times 2 is 20, minus 13 is 7, times 2 is 14, minus 14 is 0. So that confirms that 2 is an actual 0. It also tells me that our polynomial factors to x minus 2. And then we always go down a power, so 1x to the fourth minus 2x to the third plus 0x squared, I'm going to go ahead and write it, plus 10x plus 7. But that's not fully factored, and that doesn't give us all the zeros. So that we really can't factor this any further by hand, so let's go ahead and use the next one that we know. Because we know another one, we know -1. I'm going to divide -1 into the remaining numbers, into the 1, -2, 0, 10, and 7. Don't go back to the original, because if you divide it into the original, yeah, it'll work, but we're trying to factor it down. We're trying to break it down as far as we can get it. So we need to use this. All right, so we're going to bring down the 1 times -1 is -1, minus 2 is -3, times -1 is 3, plus 0 is 3, -3, 7, -7, 0. That confirms it works. It tells us we have x minus 2 we had already. We have an x plus 1 for that. And then we have down another power would be 1x to the third minus 3x squared plus 3x plus 7. And this can't factor by grouping, so we still have to use some more division. Luckily, we understand that a bounce means a repeat. So I'm going to divide -1 again. This time I'm going to use these numbers, 1, -3, 3, and 7. Bring down the 1, -1, -4, 4, 7 minus 7, 0. Okay, I'm going to scroll all this up. Hold on a sec. All right, so we had x minus 2, and we had x plus 1 already. So these guys get to stay. This -1 tells me that we have another x plus 1. And then these numbers give me, down another power would be x to the second minus 4x plus 7. Okay, so we have this one and this one and this one are the real zeros that we can see. We have one real one and then one repeated real one. And then we need to know, there's 2 more, obviously. And if we can't see them, they're probably imaginary. So how would we solve for that? And you can use completing the square, or you can use quadratic formula. I'm going to go ahead and use quadratic formula. So this is a and b and c. X equals -b plus or minus the square root of b squared minus 4 times a times c all over 2a is 4 plus or minus the square root of negative 12 all over 2. 4 over 2 is 2. Negative 12 is 2I root 3. And 2I root 3 divided by 2 would be I root 3. So 2 plus or minus I root 3. That's two different answers because that's two different complex numbers. So our total amount is 5, and they are, if we listed them all out, we would say negative 1, 2, 2 plus I root 3, and 2 minus I root 3. There's your 5 zeros. 2 of them are imaginary, and 2 of them, or one of them is repeated, and so that gives us a total of 5. Whew. And that's it for that one. I know you were looking for your joke, and you were trying to, hear my dog bark, so there you go, a little bit of everything. All right, have a good night.